Okay, before we get into workshop, I would like to introduce a new hardware that will be used in this workshop called the SGIoT, Signal Generator Internet of Things, so that you know its functionality, and we will develop a NETPIE freeboard, and then the using with Node-RED. So here is the board and the ESP module that is used. We use the FreeRTOS software, okay, the FreeRTOS library to implement the uh, signal generator, and also it can do the fast Fourier transform in the same hardware. On the board, you see that it can generate the signal at this connector. Here I measure it using the scope, and it has the input, analog input in here. Later on, we will connect the signal generate from this board to the input and do the fast Fourier transform on the same module. And it also has the OLD for manual adjustment, which I will show you in a minute. The program is quite long because we use FreeRTOS and using the two core of the ESP32. The F3 is performed in core 0, and the signal generator is in core 1. So it will not interfere with other. Otherwise, we cannot do it simultaneously without affecting each other. One functionality of this SGIoT board is that it uses the eeprom to store the Wi-Fi and the MQTT information, so that you can change it without recompiling the program. So that is the benefit, that if you want to create an IoT device, you should somehow have that feature for the user, so that it can be changed very easily without the user have to deal with the code, which is very long and complicated. Another thing is that this board can be used either online or offline. If you don't connect it to the internet, you can use the offline mode and adjust the signal type and frequency, amplitude manually. So that is another nice thing about this SGIoT board that I will show you here. Okay, you see that at this moment, that this does mean that it cannot connect to the Wi-Fi because I haven't given the Wi-Fi information. If I place this switch, okay, it will keep trying to connect to the Wi-Fi. So you see that Wi-Fi connection about and running in offline mode. So now this board can be adjusted using the offline method. So here I show you the scope, and I will try to adjust this. Okay, now you can use you can change signal type from sine wave to, if I press this signal select switch here, it can change the signal type to square wave. Okay, let me enlarge this a little bit. This is a triangle wave, and the sawtooth, the different 6 type of signal. Okay, this is a random noise, a random signal, and the PRBS sequence. This is useful for system identification. Okay, so here I can adjust things, and when I change it to the frequency mode, you see there's a pointer in there. Okay, like index. Now I'm in the frequency adjustment mode, and I can use the Okay, I can use this VR to change the frequency. Okay, you see that? Okay. Also, if I press the here again, I can adjust the amplitude of the signal. Okay, so this is a manual mode. That means that my IoT device, if I don't have the internet connection, I can do it manually like this. Can adjust the frequency for uh, each type of the signal like this. Okay. Now, what I have to do to make this an IoT device, first I have to provide the Wi-Fi information, right? And then the NETPIE or other cloud service information so that it can connect to that service. Okay, so let's first do we can use the command method. Okay, I found that this is quite easy to adjust. For example, in this Zoom now, I have Wi-Fi SID. Use this one. Okay, so I just type Wi-Fi SID equal to my SID and Wi-Fi password equal to whatever that you are using. Okay, so the information is written to the memory, but now it is not written to EEPROM. I have to use the command save at the end. Now, suppose I want to connect this device to NetPie, I have to create a project and do the same thing that we did all the time. Okay, so I have to create a new device for this. I call it your device. Okay, maybe like this. Okay, now I have this device. Now I have to provide this client ID token secret, right? And so you say that I use the command interpreter as before, and I create the command for the Wi-Fi and the MQTT like this. So when I type MQTT client equal to the string that is generated by NetPie, it will be copied to the memory. Okay. So MQTT. Now it's okay now. MQTT user equal to now the user information is the token here. MQTT password. You see that for in Windows where you don't have to recompile the program, okay. Even though it may be a little difficult at the beginning like this, but not too hard to do. Now I have all the right command for this. Then I just type save like this to save the information to the EEPROM. Okay, it's a parameter step to EEPROM. Press reset button. Now I only had to reset the hardware here. Now you can see that now it becomes an IoT device. It can connect to NetPie and send the information to this NetPie. Okay, if I refresh this, I can see that now my device is online. Okay, I have the information written to the shadow part of the device. Before we go to the keyboard, I want to show you that this can be commanded using the serial port as well. Okay, so suppose I want to change the signal type from here to maybe square wave. I got go to one. Now I have the square wave. Okay, and I can use 6 frequency. Go to one. Right now it is about 20 hertz. If I want to change it to 1 hertz, I can do it too. So this can be adjusted using the command like this. Change it to sine wave. Okay, so you see that, and the data is updated to the NETPIE. Now we want to make a keyboard to make this easier instead of typing the command like this. So let's do that. So go to keyboard, click on keyboard and create a new one. Okay, use the name that you like. Now you can click on this keyboard and develop the widget one by one. Okay, which is quite a few because there are several variables to adjust, like. So I give you easier way to do that, and you can do it. You can do it for your user. Okay, so instead of adding the data source and add the widget, you just import, okay, the keyboard in the JSON format. So this is the keyboard that is previously saved. That is already made and previously saved. Okay, you have to open this file first. Okay, this is a template, and you can see the code in JSON format like this. It look quite complicated, but the only thing you have to change is here. Okay, you have to fill in the device ID and token to here, and then import it to the keyboard. Now you have the working keyboard without doing it by yourself. What we have to do is we put the client ID here, copy, and put it in the device ID here. Okay, just paste it. Replace the template that I use. Okay, the underscore token and underscore client ID. You just replace that. Okay, with the information from that part. Now you have the information that you need. But the some name, you can change that or not. It doesn't matter. But if you have to change, you must change it for all in this widget area. Okay, that's on name here. So you have to use the file and replace facility of your editor. But this will work fine. Okay, so just save that to some name. Okay, so maybe I save it to this one. Okay, and now what I have to do is I only have to import that to my keyboard. So it's like here. Now we have the whole keyboard. It's that's working. It may be some arrangement of the widget may be mixed a little bit. So you can just move it to the location that you like. Let's say you should look like this. Okay, and which one might be here. Okay, and you can adjust it easily. Now I want to show that if I want to test if this is working or not. So let's try to change the signal. Now you see that the signal can be changed using this toggle switch. Okay, triangle, the sawtooth. I can adjust the frequency. So this keyboard is working quite okay. You see that, and amplitude can be adjusted. Okay. To test the FFT, I have connect the signal generator to the analog input of the board like that. If you are not familiar with the fast Fourier transform, this slide may help you. You see that for the sinusoid wave, if you do the FFT of this sine wave, you will have only one peak, like, and the frequency of the peak equal to the sinusoid frequency. For the square wave like this, you will have the base frequency of the square wave and the third harmonic. Okay, so the base frequency is 100 and the third is t time of that. For the triangle wave, okay, you have the base frequency and the harmonic is very small. Okay, actually for the square wave, you will see the fifth harmonic right here. Okay, with 5 times the base frequency. For the sawtooth, you will have this. Okay, the base frequency and second and third and fourth harmonic like this. For the random signal, the peaking is also, it cannot be predicted. It's quite unpredictable. Actually, for the true random variable, you would have flat, like the flat frequency response. But we will see that from this 4 type signal, the Fourier transform should show, should show that. So get back to our setup here, and so I want to show you for the square wave, you will have the base frequency and c time. Okay, the third harmonic, like so c time, the base frequency is about 30 hertz like this. And for the sawtooth, you will have the base frequency, the second, the third, the fourth harmonic. So let's see if that is the case. See, you can see that for the sawtooth, we have the base frequency, the second harmonic, the third harmonic, the fourth harmonic appears. So to summarize, the SGIoT hardware can do can generate the signal, 6 type of signal, and do the fast Fourier transform on the same MCU. Okay, this is possible because I can use the two cores, processing core of the ESP32 and I separate the signal generation and the FT to separate core. Okay, so it will not interfere with each other, and this works quite well. Later in this workshop, we will develop the flow for this using this hardware, and we will learn a little bit on the node rate